Welcome to Science Views from the Valley. I'm your host, Dr. Kelly Kassan. Science Views from the Valley is a monthly program that will explore interesting science topics and how they relate to the San Luis Valley and the Upper Rio Grande region. Hello and good morning on this lovely, warm May day. The weather has been nice for a couple of weeks now, so people are probably thinking about starting their gardens. I know I planted mine this past weekend. So today I would like to talk about insecticides, the different types of insecticides, what they are effective against, and how they work against pests. It may surprise you to learn that pesticides have been in use since biblical times. The first pesticide known to be used was sulfur, which was used by the ancient Sumerian farmers over 4,500 years ago. People have been using powdered elemental sulfur, a yellowish dust, since 1000 BC. The Greek writer Homer, author of the Iliad and the Odyssey, wrote about the use of sulfur to eliminate lice. Sulfur is also effective against fungal pathogens, ticks, and mites. In fact, professional arachnologists like myself will still dust the bottom of their pants with powdered sulfur to reduce the risk of ticks and mites when they do field work. Elemental sulfur is also considered natural and non-toxic, so organic farmers are able to use it effectively against fungal pathogens like the apple scab, powdery mildew, and black spot. How sulfur works against fungal pathogens, however, is still poorly understood. Researchers currently think that sulfur either reacts with the plants and the fungi to produce an agent that is toxic to the fungi, or that sulfur enters the fungal cell and interferes with cellular respiration, essentially suffocating the fungal cell. Sulfur kills arthropods directly by disrupting their ability to produce energy. Other ancient insecticides include the heavy metals like arsenic, mercury, and lead. Arsenic disrupts the cellular process that produces ATP, the molecule that is used to provide energy in cells. Because arsenic disrupts the production of ATP, there isn't enough ATP to allow muscles to fire. Arsenic was mixed with borax, a substance that desiccates insects, in insect bait traps in 900 AD. Though borax and its relative boric acid are relatively non-toxic to humans and mammals, heavy metals are known to be toxic and carcinogenic, so their use has been limited since the early 2000s. Powdered dry flowers of the Dalmatian chrysanthemum was used to delouse children in ancient Rome. Dalmatian chrysanthemum extracts were also used by the ancient Chinese and Persians as an insecticide. Europeans during the Middle Ages used this flower extract against cockroaches, bedbugs, and mosquitoes. This powdered extract, called pyrethrin today, was so effective that merchants sold the extract powder as Persian dust during the 19th century. Pyrethrin and pyrethroids, synthetic compounds that were developed that are similar to the natural chrysanthemum extracts, are still used today as insecticides. These extracts work by disrupting the electrical signals in the nervous system of animals. The nervous system of insects and other arthropods, like mites and lice, are more sensitive to pyrethrin than mammals, making pyrethrin safe to use. But be aware that pyrethrins and pyrethroids can be toxic if the chemical is ingested, one reason why they are not recommended for flea products for cats or small dogs. Household pets are constantly licking their fur, which causes them to ingest more of the chemical. This can lead to toxic overdoses. Other botanical insecticides were developed before the 19th century. These include the nicotine compounds that were extracted from tobacco plants. Nicotine is an alkaloid that is found in most nightshade plants, even the edible ones like potatoes, tomatoes, and eggplants. These plants produce nicotine as a defense against herbivores, and it's a highly effective insecticide. Nicotine mimics the chemical acetylcholine, a neurotransmitter that sends signals to other cells, including muscle and nerve cells. Nicotine competes with acetylcholine for receptors that trigger hyperexcitation of these cells, resulting in convulsions, paralysis, and death of the insects within the hour. Englishmen boiled tobacco plants in water and then painted the water on plants to eliminate garden pests. They also rubbed the tobacco water on the heads of children to kill head lice. Nicotine compounds are highly effective, but the problem is that they are also toxic to vertebrates, including humans. A teaspoon of concentrated liquid nicotine can kill a 26-pound toddler. Ingesting as little as 5 cigarettes or 10 milliliters of liquid nicotine can kill an adult. Thankfully, most people do not eat cigarettes or drink vape juice, but they should be careful to keep them in child-proof areas if they have small children in their household. Rotenone is another botanical insecticide that was isolated by the French botanist Emmanuel Geoffroy in 1848. He learned about the pesticide application of rotenone from the native tribes in French Guiana, who used an infusion of rotenone-containing plants to stun fish, which allowed them to collect more food. South American natives also use rotenone-containing plants to kill sheep ticks in Peru. South American and Caribbean plants that contain rotenone include the jicama, goat's rue, lance pod, and barbasco. In Asia and the Pacific Islands, the jewel vine was most commonly used to extract rotenone. Malayan gardeners were known to use these plants as an insecticide long before rotenone's discovery. Rotenone kills insects and other animals by interfering with the production of ATP, the molecule that is used for cellular energy. Insects and fish are particularly sensitive to rotenone because of their respiratory systems. The gills of fish and the trachea of insects allow rotenone to enter the bloodstream quickly. Rotenone is only mildly toxic to mammals because the chemical is not easily absorbed through the skin, and the digestive system breaks down the molecule if it's ingested. Human deaths due to rotenone are extremely rare because it is an irritant that causes vomiting. But in 2011, a study on farm workers that use rotenone found a link between rotenone exposure and the development of Parkinson's disease. Rotenone is still used today to remove invasive fish from lakes, but its use as an insecticide has been banned in the UK since 2009, and it is currently being phased out in the US and Canada. Rotenone is highly effective against crop pests, but it's non-selective, killing both pests and beneficial species. This creates a rebound effect. Rebound effect is when the broad-spectrum pesticides like rotenones kills the pest and the biocontrol agents like praying mantis, ladybugs, and spiders. When the pesticide degrades, the pests return, but the biocontrol agents are not there to control the pest population, so the pests rebound to much greater numbers, causing even more destruction than before the pesticides were applied. The most famous, or infamous, insecticide, DDT, was developed in 1874. DDT is one of the organochloride insecticides, along with the chlorinated cyclidines, which include aldrin, dieldrin, hepatochlor, and indosulfan. DDT and similar compounds work by preventing the sodium channel closure, which hyperexcites the nerves. This causes fatal spasms in insects and other animals. During World War II, DDT was the preferred pesticide because it was a broad-spectrum insecticide with low toxicity to mammals. DDT was also inexpensive to produce, easy to apply, and persistent. Persistence in this context means that the chemical does not degrade in the environment. DDT does not degrade in sunlight, and it was not soluble in water. This persistence, however, created a new problem. DDT can last as long as 30 years in soil and 150 years in aquatic systems. DDT is also lipophilic, meaning that it combines with oils and fats very well, including human breast milk. This characteristic of DDT and its persistence is why DDT is found in human body fat and blood samples as recently as 2005, though the concentrations of DDT have sharply declined since it was banned in 1972. DDT and other organochlorides, because of their persistence, cause biomagnification. Biomagnification is when a persistent chemical or heavy metal is absorbed or ingested by small organisms, microcrustaceans and aquatic insects, for example, which are then eaten by larger organisms like small fish. Because these small fish eat a lot of the smaller insects, they absorb more of the chemical or heavy metal which is stored in their body fat. Larger fish will then eat a lot of the smaller fish, so even more of the chemical or heavy metal is stored in their tissues. Biomagnification is the reason why only one serving of fish per week is recommended today, especially if the fish is a large predatory fish like shark, swordfish, or king mackerel. Another class of insecticides that were developed prior to World War II was the organophosphates. Organophosphates were originally used as chemical warfare in Germany during the 1930s. Sarin, a nerve agent that was used in the Tokyo subway attack in 1995 and in the 2013 attack in Syria, is an organophosphate. The organophosphate insecticides include parathion and malathion, which interfere with the neurotransmitters, disrupting the brain signals to nerve endings in the rest of the insect body. Organophosphates are highly effective against insects, but unfortunately they are also toxic to mammals and humans. Humans can be poisoned by organophosphates by drinking water contaminated with the chemical, breathing in vapors containing the chemical, or absorption of the pesticide through the skin. Farmers and others who work with organophosphates should wear protective clothing while applying the chemical and shower thoroughly before going home. Despite these precautions, approximately 3 million people per year are poisoned by organophosphates. Organophosphates are one of the causes of the Gulf War syndrome, the chronic disorder reported by veterans of the Gulf War. Organophosphate pesticides and insect repellents were used during the war, exposing military personnel to a higher than normal level of organophosphates. This toxicity is why most residential uses of organophosphates were banned by the EPA in 2001, though they are still used in agricultural and anti-mosquito efforts. Since the 1940s, a number of synthetic insecticides have been developed. These newer synthetic insecticides can be grouped into 7 different classes. I've already mentioned 2 of them, the organochlorides like DDT and the organophosphates. Another group includes the pyrethroids and the neonicotinoids, are synthetic variants of plant extracts pyrethrum and nicotine. These broad-spectrum synthetics are believed to be less toxic and less persistent than the organochlorides and the organophosphates. But because they are broad-spectrum, they are known to harm honeybees and other pollinators that are necessary for plant reproduction. Rhinoids, which include the diamine insecticides, are synthetic variants of a defensive plant chemical called rhinodine. Rhinoids act on the calcium ion channels, which are involved with muscle contractions. Rhinoids' interference with the calcium ion channels causes massive muscle contractions, leading to paralysis and death. Most rhinoids, however, are known to be toxic to bees and aquatic invertebrates. The exception is the rhinoid chemical called chlorantraniliprole, marketed as acelyprin or Grub X, which is categorized as having a low risk to honeybees. Another insecticide group is the butylenolides. A butylenolide called Savantal Prime was developed by the Bayer Crop Science in 2012. This insecticide, like the pyrethroids and the neonicotinoids, was inspired by a defensive chemical produced by plants. Savantal Prime is a nerve toxin that disrupts the insect's nervous system. Unlike the pyrethroids and the neonicotinoids, this synthetic insecticide appears to be considerably less toxic to honeybees and other pollinators. It is also less toxic to beneficial insects that help to control pest insect populations, like ladybugs and lacewings. This reduces the risk of a rebound effect. This insecticide is marketed as a pesticide that targets plant-sucking insects, which include the aphids and scale insects. While all of the above insecticides work by killing the pests, resistance to the insecticide is one of the drawbacks. Insects become resistant to insecticides because none of the insecticides I've mentioned is 100% effective. A few resistant insects will survive and reproduce, creating a new population of resistant offspring. As the insecticide is used again and again, more and more of the new generation of insects will be resistant to this insecticide. DDT, as I mentioned, was used heavily until 1972. But insect resistance to DDT was first reported in 1938. DDT-resistant mosquitoes were first reported in 1959. Today, DDT is more effective as an insect repellent than an insecticide due to the high frequency of insect resistance to the chemical. Multiple resistance to several different insecticides is now commonplace. A study in 1987, for example, found that at least 447 insect species were resistant to DDT, organophosphates, and pyrethroids. This issue led to the development of insect growth regulators. Two types of insect growth regulators have been developed: those that mimic juvenile insect hormones, which interfere with the molting process that occurs as juvenile insects grow, and those that disrupt the synthesis of chitin, which is the primary component of an insect's exoskeleton. Methoprene, pyriproxyfen, and phenoxycarb are examples of the hormone-mimic IGR, while diflubenzuron is an example of the IGR that disrupts the chitin synthesis. Hormone mimics prevent juvenile insects from reaching maturity, so they cannot reproduce. Chitin disruptors cause insects to die when they molt, since they cannot produce a functional exoskeleton. Insect growth regulators may also prevent insect eggs from hatching. IGRs also affect the pupa, also known as the cocoon, in mosquitoes, beetles, moths, and other insects that have pupal stages. The IGR prevents the metamorphosis of the juvenile within the pupa into an adult. Insect growth regulators mimic hormones that do not occur in mammals and humans, so they are relatively safe. IGRs are also relatively safe for the environment because the chemical degrades rapidly in sunlight. Low levels of IGRs also appear to have a low negative impact on aquatic insects, except for those closely related to mosquitoes like midges and gnats. IGRs, because they disrupt the life cycle of pest insects instead of killing them, are slow-acting but are quite effective. But they can also negatively affect honeybees and other pollinators by interfering with the development of their larval stages into adults. The 1980s and 90s saw the rise of genetically modified foods, called GMOs, that included plants that were genetically modified to produce extra chemical defenses against pest insects. One of the first GMOs to be approved by the FDA was Bt corn. Bt corn is genetically modified by inserting a bacterial gene that produces an endotoxin that is known to kill corn earworms and corn borers. Because the bacteria that naturally produces this endotoxin is a common soil bacteria, it was believed to be safe for human consumption. This GMO proved to be quite successful, so much so that the Bt gene was added to cotton, soybeans, and potatoes. Bt corn currently makes up approximately 92% of all non-organic corn sold in the U.S. 94% of soybeans and cotton are also genetically modified to contain the Bt gene. Though Bt crops are safe for mammals and humans, there is some concern that it can affect non-target organisms. Since corn pollen is wind dispersed, it can fall on other plants like milkweed, which the monarch butterfly larvae feed on. Another problem with Bt corn pollen is that it can pollinate other maize species. For this reason, Bt corn crops are restricted in areas where wild maize grows, like in Mexico. Now that we have talked about the different types of insecticides, both natural and synthetic, what insecticides are allowed in organic farming? To meet the United States Department of Agriculture regulations, organic produce must be grown without the use of synthetic herbicides, pesticides, fertilizers, or GMOs. Organic plants cannot be genetically modified. The USDA has 4 levels of organic labels: 100% organic, organic, made with organic, and specific organic ingredient listings. 100% organic is restricted to products that contain 100% organic ingredients. These products must be certified by a USDA agent to make sure that the organic farmer is following all USDA regulations for organic products. Organic labels are used for products that contain 95% or more organic ingredients. The other 5% may be non-organic, but these ingredients must be listed on the national list of allowed and prohibited substances. Made with organic labels are used for products that contain at least 70% organically produced ingredients. Any other product, if they contain at least one organic ingredient, that ingredient can be labeled as organic in the ingredient list of that product. Organic produce, however, is not pesticide-free. Examples of pesticides used by organic farmers include plant-derived chemicals like neem oil and caraway oil. Boric acids and elemental sulfur are also allowed. But many organic farmers use crop rotations, trap crops, and biological control agents like ladybugs and lacewings for pest management. I hope you found this information useful in helping to decide which pesticide methods are best for your purposes. Even if you do find that you must use a pesticide that harms bees and other pollinators, try to avoid using it when the plants are in flower. This will reduce the pollinator's exposure to the chemical. My next show will be on June 24th, a mere 3 days after the summer solstice. I will be talking about extremophiles, organisms that live in extreme environments that would kill most other organisms. These will include the bacteria and archaea that live in geysers, the salt-tolerant species that live in the Great Salt Lake and the Dead Sea, and sulfur-tolerant species that live near volcanic vents located on the ocean bottom. As always, if you have a topic that you would like to hear discussed on this show, contact me at spiderwomankrza@gmail.com. If you would like to hear my past shows, they are archived on the Science Views from the Valley channel on YouTube. I would like to thank everyone here at KRZA for their support for this show, and I hope that you will be tuning in to listen next month.